Now, the good news is building a neural network using these concepts isn't quite as difficult as it sounds. So it turns out that the operations behind a neural network, where you're taking this list of neurons here and multiplying them together with all the neurons above it in another layer, mathematically, that's identical to doing a matrix multiplication and a bunch of vector additions when you take into account the bias neurons. So mathematically, you can represent a neural network as nothing more than a set of matrix operations. And guess what? GPUs were built for this sort of a thing. When you're doing 3D graphics for a video game, what's really happening there is that you have a bunch of 3D objects that are being transformed with matrix operations all over the place. So GPUs, by a happy accident, are purpose-built for doing exactly the same kinds of mathematical operations that we need for running a neural network. So that's kind of incredible, right? Kind of a happy accident that the technology we built so you can play your favorite video game quickly can actually be repurposed to build, artificial brains in some way of speaking. So if you were to create an artificial neural network in TensorFlow at a low level, you could just say tf.matmul, that's a matrix multiplication of one layer and the weights plus the biases, and that would just be how you connect two layers together in a neural network. It's that simple. But you don't have to think about neural networks from a mathematical standpoint with TensorFlow, where this is kind of doing it the hard way. And before Keras came along, that's how we had to do it. But thankfully, we do have Keras. It used to be that Keras was this extra package that you had to install alongside TensorFlow, and it ran on top of it. And at that time, sometimes Keras could be a little bit slower than using TensorFlow at a lower level. But as of TensorFlow 1.9, TensorFlow has included Keras as part of itself. So you now have the Keras API, which is purpose-built for building deep neural networks, as part of TensorFlow itself, and it's super fast and super easy to use. So there's really no reason for you to have to go down to a lower level and think about neural networks in terms of linear algebra anymore. You can just use the Keras API, and there's a lot of good reasons for doing that. First of all, with Keras, we have built-in integration with scikit-learn, so you can actually treat your neural networks as any other scikit-learn model. You can do cross-validation on them and just evaluate them like you would any other model in scikit-learn, which is kind of neat. It's also a lot less for you to think about. So because all the nitty-gritty details under the hood are being hidden from you, the decisions have already been made on how to best optimize those operations, so you don't have to think about them. And it's one less thing for you to mess up, right? And this makes it a lot faster to prototype new ideas and try them out. And that is really what's most important about the higher level Keras API, because the faster you can experiment, the better your results will be. Really, most of the work that you're doing in the field of deep learning is just trying different topologies, trying different approaches, trying different parameters, tuning your hyperparameters, and just trying to get through experimentation the best results you can get for the problem that you have at hand. And the faster you can iterate on those ideas, the better your end result will end up being. Because in reality, you only have so much time to devote to a given problem. So the faster you can try different solutions to that problem, the better solution you'll end up with. And that's really why Keras is so important. Now, you've had a little bit of exposure to Keras previously in the course, so you've seen how it works at a high level. Let's dive into some more specific examples here in a little bit more depth. For example, if we're doing a multi-class classification problem, an example of that might be trying to classify images to see what street signs they might contain. So maybe you have an image that might contain a stop sign or a yield sign or a school crossing sign. That's an example of multi-class classification because stop sign, yield sign, and school crossing sign are all different classifications, and there are several of them to choose from. Multi-class classification. And setting that up in Keras is really simple. So all you need to do is start by saying you're going to build a model that is a sequential model. That just means we can build this model up one layer at a time. We can add the first layer to our neural network, thusly, and we can say we have an input signal of 20 neurons coming into it. For an image, that would be a very small number. I mean, you don't have very many images that just have 20 pixels, but imagine you did. We can specify the activation function we want and just specify that with a little string here. And we're going to say that's going to go into a hidden layer of 64 neurons. Then we're going to add another hidden layer of 64 neurons as well. And then we'll add the output layer of 10 neurons, if we have, for example, 10 classifications to choose from, with the softmax activation function to actually do that choosing. And there, we've actually constructed a deep neural network with 3 lines of code. The entire topology has been defined there, along with the activation functions we want to use. Now, to actually run it, we need to also specify our loss function. And in this case, we're going to say it's categorical cross entropy. And again, there are several to choose from. That's generally a good choice for multi-class classification, though. You can choose whatever optimizer you want. In this case, we've manually configured an SGD optimizer, but you can also just specify a string there as well if you just want to save some keystrokes and don't need all that extra control over the hyperparameters behind your optimizer. And finally, we'll define what metrics we want to measure as a measure of the success of our model, and then you compile the model and run it. That's it. So this would have been a whole lot more code just dealing with TensorFlow at a lower level, but you can see how Keras makes it very easy to try out new ideas and new topologies for a given deep learning problem. Let's look at another example here for binary classification. If I just have two classifications to choose from, yes or no, or is this something or is it not a thing? Very similar approach here. Again, we're just going to have a sequential model. We'll have 20 input neurons and 64 hidden neurons, and again, that will obviously change depending on the nature of your data with a ReLU activation function. We'll add another hidden layer of 64 neurons and another output layer here. And obviously, since it's a binary classification problem, we only have one output neuron on the output layer. It's just going to be 1 or 0 at the end of the day. And we're going to use the sigmoid activation function this time instead of softmax. So remember back when we talked about logistic regression. We talked about the logistic function, which is also known as the sigmoid function. And again, that's just a way of converting the output of this thing into an actual probability of being yes or no. So same exact trick that we did in logistic regression to get a binary yes or no answer out of our deep neural network here. These things all kind of tie together in cool ways. We will also compile that model, this time with the binary cross-entropy loss function. And the optimizer can be whatever you want. You can see that in this case, we just specified it with a little string using the default values. RMS prop is a popular one. Atom is also really good. And we specify the metrics that we want to keep track of while we're actually running it. And that's it. There's an example of binary classification. Only difference from multiclass was our choice of loss function, the sigmoid activation function with a single neuron at the top layer, and that's pretty much it. It's important to note that you should always make sure your features are normalized, so all the inputs going into the bottom layer of your deep neural network need to be on the same scale. Generally speaking, you want them to actually be with a 0 mean and a unit variance around them. But the real thing that's important is that every input feature is comparable in terms of magnitude. So for example, if you had a neural network that was trying to classify people based on their age and their income, the age might range from 0 to 100, but income might range from 0 to 1,000,000. Those are wildly different ranges, so that's going to lead to real mathematical problems if you don't scale them down to the same range. Fortunately, scikit-learn has a standard scalar function you can use to make that really easy, and a lot of the data sets that you experiment with will be normalized to begin with. I mean, really ideally, you would want your data to be pre-processed before you're feeding it into your neural network at all, and hopefully that's being done at some stage before it actually gets to you. But it is important to check that your inputs to the same neural network are all scaled in the same way and comparable in terms of their values. The math just does not work out otherwise. Let's go into some more detail about how classification really works at the output layer of a neural network. So let's focus on the top of this neural network here. So the top layer is going into 3 output neurons, and this is an example where we might have 3 different classifications to choose from. Maybe we're trying to classify images as being a dog or a cat or a horse, right? Now, the way that we translate the outputs of these neurons, which are just some weird floating point value at the end of the day, into an actual classification, takes a couple of steps. The first thing we do is pass them all through a softmax function, and this is just a little mathematical function we talked about earlier that converts those outputs into actual probabilities for each classification. So what I'm going to get out of softmax will look something like this. Maybe I'll get a 70% chance that it's the category 0, and a 10% chance that it's category 1, and a 20% chance that it's category 2. So in this case, we would choose category 0 as the most likely choice there. And let's say that while we're training this neural network, that is in fact the correct answer. That's the correct label, category 0. So one-hot encoding is a way of encoding that category number, that category label, as a binary representation. So for example, category 0 would be represented as 100 in one-hot encoding. And you can see why we're doing that here, because that aligns up with the output of softmax very nicely, where we just have 3 neurons, each of which conveys information about a specific classification, and our encoding needs to represent which of those 3 output neurons represents the correct classification. So it's important to realize that we can't just deal with category numbers like 0, 1, and 2 directly when we're dealing with neural networks. We need to one-hot encode them into this binary representation so we can match those up with the actual neurons coming out of our neural network. Let's look at a few examples here. So for example, if I had category 0, the 1 hot format of that would be 100. Category 1 would be 010, and category 2 would be 001. Got it? This is different from binary representation. It's just sticking a 1 in the position that corresponds to the category you want, and we use this format because it aligns nicely with the way neural networks work. So with all that, let's try it out and actually use Keras to solve a classification problem actually using TensorFlow on your PC.